So let's go through a few of these factoring problems that I have in the notes. Work through these step by step so you can kind of see my thought process I'm going through and solving in the notes as well. So the first type of problems we're going to look at are what I call just the basic factoring problems. These are factoring problems where we're going to factor it by finding a common factor in all of the terms in the expression and then doing a reverse distribution property to actually pull that term out to the front. So for example, in these three terms, the common factor is 2x. So I can actually just think about pulling a 2x out to the front and then ask myself, what would be left in each of these three terms if I pulled this 2x out? In other words, what should I multiply the 2x by to get back to each of these terms? So for example, the first one, if I want to multiply 2x times something to get back to 2x cubed, I better multiply it by x squared. If I want to multiply 2x times something to get to negative 12x squared, I should multiply it by a negative 6x, and then I should multiply 2x times a positive 3 to get back to 6x. The idea is that we're basically doing the reverse of the distribution property, where I could go back and actually distribute this 2x out to all three of the terms in this expression and get back to my original expression. And in general, that's how all of these factoring should work. You should be able to tell whether or not you did it correctly, because if you multiply it back out, you should always get back to the original expression that you started with. So let's try another example that has a few more variables in it. This one, 18a to the 4th b squared minus 30a cubed b cubed. Again, the way I'm going to figure out what the common factor here is, I'm actually going to go through each of the constants first and figure out, well, in this case, the greatest common factor I can pull out is a 6 out of 18 and 30. And then I'm going to look at each of the variables individually. So a to the 4th, a cubed, the greatest common factor will be an a cubed that exists in both of them. And then b squared, b cubed, so I can pull out a b squared. And then I just ask myself, what would be left over if I did this? Well, here I should have a 6 times 3 to get back to the 18, and then I need one more a to get back to a to the 4th, and I don't need any b's to get back to b squared, so my term here just becomes 3a. Here, I need to multiply by a negative 5 to get back to negative 30. I already have 3 a's, a cubed, so I don't need any more a's here, but I do need one more b. So my expression becomes this, 6a cubed b squared times 3a minus 5b. And again, you could distribute this back out and you should get back to the original. The idea of all this factoring is we're taking something that's only split up by addition and subtraction, and we're turning it into an expression that's split up somewhere by multiplication. Now this won't always work, because in your expression you might not necessarily have a common factor that is in all the terms, except for 1. You can always pull a 1 out, just like you can always multiply by 1 and not change the expression. But if you look at this particular expression, there's not a common factor other than 1 that exists in all 4 of these terms. So we run across this problem, we have another technique that we can use to try to factor this, and this is called grouping. The idea is that if I group these in smaller groups, the groups will have common factors, and then I can try to factor common factors out of these smaller groups. For example, here I have 4x cubed minus 4x squared. I could definitely factor out a 4x squared as a common factor, and I'll be left with x minus 1. And then here, 3x minus 3, I can factor out a positive 3, and I'll be left here with x minus 1. And what we want to happen is that both of these expressions end up being exactly the same. Because now what I can think in my mind is, well, now this is a term, and this is a term, and within this term, these both have a common factor of x minus 1, because x minus 1 is multiplied times the other part of the term. So it's more complicated, but still just think it's something times something, something times something, and these two things are exactly the same. So what that means is if I have two parts of the term that are exactly the same, a part of the expression that are exactly the same, I can actually factor that out to the front. So I'm going to factor out the x minus 1 now. to the front, and then what am I left with? Well, I'm left with a 4x squared here, and a plus 3 here. And so now I actually have a factorization of this original value. And if I go back and FOIL this together, I should get back to this original expression. Now, the factoring by grouping, it doesn't necessarily always work with the first grouping that you have, the natural grouping. Sometimes you might have to move things around and get them to group that way. So that's all right. If it doesn't work out at first, so maybe you factor this and these guys don't end up being exactly the same, just back up a step and try to move some of the terms around and then group it again and see if you can get it to work. Let's try another one. This one, 2x cubed minus 4x squared minus x plus 2. Again, I'll just try the natural grouping first. So I'll try grouping these two together and these two together and see if this comes up with something that will help me. So 2x cubed minus 4x squared, I can pull out a 2x squared from both of these, and that'll leave me with an x minus 2. Now the trick here is that here I have a negative x plus 2, and here I have a positive x and a minus 2. I would actually like to switch both of these signs. I would like for the 2 to be negative and the x to be positive, so it becomes the exact same expression I have right here. And I can do this using a trick of factoring out a negative 1 from the expression. Because if I factor out a negative 1, this will become a positive x, it will change the sign, and this will become a negative 2. The way you can convince yourself that that's okay is because if I went back the opposite direction, if I distributed out this negative 1, I would get back to my original expression, so this is totally fine. And now you can see the reason I did that is because now this is exactly the same as this, which means I could factor this out to the front. So I'll factor the x minus 2 to the front, and then I'm left over with a 2x squared minus 1, and this becomes the factorization of this expression. So let's try one more. This one, y cubed plus 9y squared plus y plus 9. Again, I'm just going to try the natural grouping first. So I'll group these two and these two. If it doesn't work, move some things around and try grouping it in a different way. But in this case, I can pull out the y squared, and then I'll be left with y plus 9. Now here, I already have the y plus 9, but I need something factored out to make this work. So the trick we can use here is just think about factoring out a 1. And if you factor out a positive 1, it actually doesn't change this value. So this is kind of a trick I can use to keep this expression the same, but still have something here that's factored out. So I factored out the y plus 9. I can factor out the y plus 9 from each of these terms in the expression. And now I'm left over with y squared plus 1. Again, I can always check this. Right, by foiling these together, y times y is y cubed, y times 1 is y, 9 times y is 9y squared, 9 times 1 is 9. And I should end up with the exact same expression. I might have to move some terms around, but this is an equivalent expression to the first expression that I started with. So in addition to that, factoring by grouping, we have another technique that works with a certain form of expressions. Any expression that can be written in this form, u squared minus v squared, we say this is a difference of squares. And anything that can be written as a difference of squares can always be factored into this form. The first thing plus the second thing times the first thing minus the second thing. So if you can get it to something squared minus something squared, it's just the first part plus the second part times the first part minus the second part. So a simple example would be something like this, x squared minus 9. The first thing to do is just rewrite this so it's in the form of something squared minus something squared. So I'm just going to actually rewrite this as x squared minus 3 squared. And now all I have to do is follow my formula. If I have something squared minus something squared, I just need to take the first thing plus the second thing, and then the first thing minus the second thing. And x plus 3 times x minus 3 should FOIL back to get you x squared minus 9. In fact, it should. See, x times x is x squared, x times negative 3 is minus 3, 3 times x is positive 3x, and 3 times negative 3 is negative 9. And the middle terms cancel out, and I'm just left with x squared minus 9. So this is a really simple case. Let's look at one that's maybe a little more complicated. If I take this expression, 4x squared minus 36y squared, this is also a difference of squares. I just have to do some rewriting first. For example, I could write 4x squared as 2x quantity squared. If I square that, I'll get back to 4x squared, so that's fine. And I could write 36y squared as 6y all quantities squared. So this works as well. So once you get into this form, it's easy. Just rewrite it in the form we have up here. The first thing, which is 2x, plus the second thing, which is 6y, times the first thing again, which is 2x, minus the second thing. And this should be a factorization of 4x squared minus 36y squared into 2x plus 6y, 2x times 2x minus 6y. Okay, how about one like this? So your constant terms don't necessarily have to be whole numbers in order for this to work, or perfect squares. For example, I could definitely rewrite 1 as 1 squared. That one's not too bad. But 4/9, I can also write this as a square. I could write this as 2/3 squared. 2/3 times 2/3 is 4/9. And then I need the x in here also. So I can write 4/9 x squared as 2/3 times x quantity squared. And actually I've turned this into a difference of squares. So now I can actually rewrite this as 1 plus 2/3 x times 1 minus 2/3 x. So sometimes things will work as differences of squares even if they don't look necessarily like differences of squares right from the beginning. We could even extend this idea if we wanted to something like this. X squared minus 5. You might look at this and say, well, it's not a difference of squares because 5 isn't a perfect square. But we can kind of bend the rules a little bit and say, well, isn't 5 really just the square root of 5 squared? Sure. And so in that case, we could actually split this up like this. X plus the square root of 5 times x minus the square root of 5, and still get a factorization of this particular expression. So you won't see a whole lot of these when you first start doing this factorization, but this can come in handy when you're simplifying algebraic expressions maybe farther down the line. So it's kind of a good trick just to remember and to kind of keep in the back of your mind. Now I can also extend this to expressions that are squared, not just monomials. So something like this, 2 minus x squared minus 5 plus y squared. Again, I claim this is a difference of squares because it's something squared minus something squared. We don't necessarily care what this is. It's still a difference of squares. So if you want to think about this, it's blah squared minus blah squared. So it'll just be the first thing plus the second thing times the first thing minus the second thing. So in this case, the first thing is a 2 minus x plus the second thing, which is a 5 plus y. And then all of that times the first thing, which is a 2 minus x, minus the second thing, which is a 5 plus y. And then you would just want to clean this up. So I can distribute this plus sign, and I'll just end up with 2 minus x plus 5 plus y. And then 2 minus x, distributing this negative, I'll get minus 5 minus y. And then we can just combine any like terms. So 2 plus 5 is 7, and then minus x plus y. 2 minus 5 is negative 3, and then minus x minus y. So I was actually able to take this expression and factor it out into 2 trinomials. So that's also a possibility of something that might happen. It is important to remember there's no sum of squares formula. For example, something like this. x squared plus 16, even though this is 4 squared, this won't factor. It only works when you have a minus sign right there. So don't fall into that trap. This one we actually can't factor. So keep that in mind when you're doing these problems. So we have a similar rule if we have cube terms that gives us a way to factor. So for example, if we have something cubed plus something cubed, that means we can just take the first thing plus the second thing, and then all of that times the first thing squared minus the second thing times the first thing plus the second thing squared. And then there's a similar rule for a difference of cubes. This one is almost exactly the same. The difference is that these signs change. So be careful that you don't mix up the rules and use the wrong one in the wrong spot when you're doing the factorization. So this works in a very similar way to the difference of squares. If we have something like this, x cubed plus 27, if I can rewrite this as something cubed plus something cubed, then I can use this formula to split this up into individual factors. And in fact, I could, because 27 is just 3 cubed. So because of that, I can actually just follow this particular formula. In this case, my x will be the u, and my 3 will be the v. So this should be able to factor into x plus 3, the first thing plus the second thing, times the first thing squared, so x squared, minus the first thing times the second thing, and then plus the second thing squared. And then I want to clean this up a little bit. So I probably write this as 3x, and then 3 squared, I can just write this as 9. So in this case, it actually factors out into a binomial and a trinomial. And it's kind of strange because this looks a lot simpler than this. But again, we're going to see in the future why it's sometimes convenient to be able to rewrite it in two things that are multiplied times each other instead of having just an expression with addition and subtraction. So this, if I factor this out, if I FOIL this out and multiply everything together and then combine all my like terms, I should end up back with this relatively simple expression. A slightly more complicated version of this would be something like this: 64x cubed minus 8y cubed. Again, just go ahead and write this as something all cubed minus something all cubed, and then we can use our difference of cubes formula. So 64 is really just 4 cubed, and so 64x cubed is 4x quantity cubed. 8 is really 2 cubed, so I could rewrite 8y cubed as 2y, all of that cubed. And now I can use, this is my u and this is my v, that I can just plug them into this formula. So I should take 4x minus 2y times 4x, all of it squared, plus 4x times 2y plus 2y, all of it squared. Now at this point, of course, you want to go back and clean this up and write it a little nicer. So this one's okay. 4x squared will just be 16x squared. 4x times 2y, this will be 8xy, and then 2y quantity squared will just be 4y squared. So this is a good factorization of that.